Okay, welcome to the notes here. We're going to talk today about writing polynomial graphs or writing the polynomial function from a graph. That's our goal with this. Essentially, we're going to do the opposite of what we've been doing, which was taking the polynomial, finding all the important information, and then graphing it, or sorry, sketching it. So we're going to work backwards. So let's go ahead and start there and talk about the critical points slash information that we're going to use here. So you can see that we've kind of had them answered on the left here, but let's talk about what each piece is and then kind of work from there. Obviously, one of the first things that you're going to want to find are the zeros on the graph. So you're going to go ahead and identify the zeros. Those are pretty easily identified because there's the x-intercepts. So I find them, label them. What we're going to do with those is the easiest way to describe is to say unsolve them, make them back into linear factors. Okay, that way we've got two pieces. You'll find with this function here, just for an example, I can see that I've got 1, 0 here and 1, 0 here. If I unsolve those, so x equals -4, if I unsolve it, if I go backwards, I'm going to find out that x plus 4 is true. And vice versa for this one. If I unsolve x equals 5, because that represents the root, I'm going to go back to the linear factor of x minus 5. So that will be the first step, and you'll notice that right away, if you look at the highlighted part there, I've kind of got the start of a polynomial already. You'll notice down below, though, we have to take note of how the function goes through those intercepts. If it's a crossing intercept, we know that that degree of that linear intercept is odd. So it could be 1. We'll default to the lowest value. So if it's crossing like this one here at 5, 0 is, we're going to go ahead and say that that degree is 1. Okay, until we know a little bit more, and we'll talk about that when we talk about number 2, which is the actual degree based off the turning points. But for now, the intents purpose, we'll say it's 1. And if we look at the other one here, the other intercept here is touching. It's a bouncing 0. It hits the intercept and then it comes right back off. We know that those are even, and that means it really does have to have a multiplicity of some sort, because the only way that you can have an even degree or a bouncing or touching is that if there's more than one, and that represents multiplicity. So this one we know is at least a minimum of 2. And we'll start low and we'll change those degrees based off of the next part, which is how do we know what the degree of the polynomial is? I mean, just because it wiggles like this, it looks cubic, doesn't mean that it is. This could have a multiplicity higher than 2. It could have a multiplicity of 4 or 6. How do we know? Well, that comes down to the number of turning points. Remember, the number of turning points in a function, again, turning points or relative minimum and maximum, would be outlined by, let me grab a new color here, we'll just grab black, these locations here, where the function changes direction. So it's increasing, and then it hits that point, and then all of a sudden it's decreasing. So we'd call that a turning point. And vice versa, it's decreasing up until this point, and then it starts to increase again. So you count the number of turning points. We know that it should be 1 less than the degree. So if we take the number of turning points being 2, and we add 1 to it, that's going to tell us our degree. So now we've got our degree of 3 here, which then we can confirm our multiplicities that we were kind of estimating before. 1 plus 2 does make a degree of 3, so we're good with those. We don't need to change the multiplicity there. So that kind of works in a balance. You want to start low and then work your way up to the combination that fits the degree. All right, which brings us to the last little bit that we have to pay attention to is with the end behavior. Now, the end behavior is what happens on the ends, quite literally what it says. This is something that you should be familiar with at this point. So we're going to look at this, and we know that the left side is low and the right side is up. And if you remember in our notes, if they're opposite, that gives us a piece of information. If it's opposite direction of end behavior, that they are odd. So we know that this is an odd degree. We can already see the degree is odd by our turning points. If they're the same direction, they're going to be even. So just kind of reinforce, or another way to get that information. The other part, though, is we need to decide if it's a positive or a negative leading coefficient. Okay, so that's going to be the first term of your function. If there was an a here, we need to decide if it's negative or positive. If the right side goes up, if you remember this from our notes, if the right side goes up, then we know that it's positive. If it's even, both sides go up and it's positive. If it's odd, the right side goes up, the left side starts down, and it's increasing from left to right. So either way, the right side goes up, it means that it's positive, and if the right side goes down, that means that it's negative. So in this case, if we look at the right side, it's going up. So that means that this is a positive polynomial. Now, we can also, again, we know that it's 3 and it's positive, so it's odd. So if here's the one thing that we kind of have to make an assumption for, at least at our level. In different levels or different math parts, we're not going to get into it here, but we're going to make the assumption that that A is 1, either positive or negative. So I guess I should say 1 or -1 there. We're not going to go and try to find A or plug points in. We're going to keep it simple for now and just kind of get the idea of sketching it back in. So we know that this is positive, so we don't have to change our function. So that will be our polynomial function there. Okay. So let's do one from scratch where we don't see any information and see if we can work backward. This kind of walk us through everything that we just talked about. So we see here that we've got some, let me zoom in a little bit. So we can see a little bit closer. So we've got some zeros here, so let's go ahead and identify those zeros, right? So we've got crossing zeros at, looks like 5. So I'm going to say x equals 5, positive, and it looks like I've got one at 15. Again, another crossing 0 there. Our touching 0 here, I'm going to erase that so I can see it. Looks like it's at 2. So we've got a touching 0 at 2. Again, that's going to have some form of multiplicity. I'm going to guess at least a 2, right? It's got to be even, so we'll start with a 2 and then we'll up it as we go. So the degree is going to come from the turning points, so I'll change my color here. I'll grab a little bit more dramatic of a change of color. We'll say green. Here's a turning point, again, increasing to decreasing. Here's another one, decreasing to increasing, and here's another one. So we've got 3 turning points. We know that the turning points is 1 less than the degree, so we're going to go ahead and say that the degree of this is a 4. Now, to kind of add into that, we know that if it's an even degree, that our arrows should be going in the same direction, either both up or both down, if we're saying it's even. So let's verify that information by looking at the end behavior real quick, and we can see that they're both going down. So that confirms that piece of information. So we know it's an even degree, some sort, and we know that it's a degree of 4 based off the turning points. All right, so we could start to write the equation, but let's go ahead and fill in the other piece of information before we do that. This is what's the sign of the leading coefficient, and for the leading coefficient, we know that the right side's going down, so we know that it's going to be negative, and we know that that leading coefficient is even because we found that already by the degree. How do we know? Based off degree. Off degree and end behavior, I guess we should say. Okay, just kind of making sure that you're paying attention there. So go ahead and let's write or unsolve these zeros and see if we can put this whole polynomial together. So if x equals 5, if we unsolve it, we'll subtract to the other side. We'll find that x minus 5 is one crossing linear factor. And then if we take the other one and we unsolve 15, x minus 15 is one crossing linear factor. So we know there's some degree, some odd degree because they're crossing. So when we got one more 0 to deal with, and that's x equals 2. If we unsolve that, I'm sorry, that should be a -2 because that's there. So that should be x plus 2 for that one. And we know it's got to have a minimum of a 2. Now we can increase those to match our degree, but let's go ahead and count. I think we're good. Here's two linear factors, so 2, 3, 4. If we multiply those out, we get a degree of 4. So we're good right now. We know that the a value here is, we'll have to sneak it in there, a -1. So that whole thing would be multiplied by a -1 because it's flipped upside down. So that would account for it. And again, assume for our purposes that this is, the a is equal to -1 in this case, the 1 or -1. All right, I'm not going to do the back page of the notes because I feel like it covers everything that we need. That's just a couple of areas. I'll put the other page of notes if you want to see them into the OneNote so that you can copy them down and or ask questions on them if you'd like to. So otherwise, I'll see you in class. Thanks for listening. We'll talk to you later.